Morning everyone, Miss Butler here. I have a video for you on titrations. More specifically, we're going to look at weak acid and strong base titrations in this video. Alright, for this video, you're going to need a couple things. There should be a note page, and really the note page for you guys is going to have a few practice problems, some graphs to look at. The main thing you're going to take notes on is a page that looks like this. Mine is all filled out, but it's going to be a graph with a bunch of beakers and room for you to write some information about the equations. And then you're going to need at least 3 color markers or colored pencils or something to draw your particle drawings with. So definitely 3 colors, maybe 4 if you want your calculations to be in a different color, your notes and labels to be in a different color. Alright, so you should have a document that looks like this for our weak acid and strong base titration, so you can see the curve of the graph. I encourage you to write this generic equation. So HA represents our weak acid, OH minus represents our strong base. We donate that H, and that's how we get our water. And what's left over is our conjugate. So we have our weak acid, and we have a conjugate base right here that can't be canceled out because remember, weak acids, even though they're aqueous, we do not split apart in the net ionic equation because they do not break apart 100%. So this A minus cannot be canceled out, so it is part of our balance equation. So write this generic balance equation nice and big on the top, and then we also need a key. So we're going to draw particle drawings in all of these beakers. So here is your key. Again, you need 3 different colors to help you. So I'll give you a second, maybe make your key off to the side. I did kind of use this space to write equation stuff. So on my document, I actually wrote the key nice and small up here, but that's totally up to you. But you will need room underneath each beaker to write some information about the equation. So the smaller the key, the better. Okay, so we're going to start with this green dot right here. That's beaker number 1. So this is before the titration actually happened. So on your graph, we have the pH, and that's the pH of this beaker, and then the milliliters of the strong base that are added. So over time, we're going to add little drops of NaOH to this, and we can measure that volume and see how the pH changes. So at the very beginning, when there is no NaOH added, all we have is a bunch of this HA, this weak acid. So let's say that I'm starting with 12 particles of solid HA, and we're going to just dissolve it in a certain amount of water. So this is now aqueous, it's dissolved in water. I'm not going to show that extra water. I'm only going to show the water we make. But as you can see, I have 11 particles of HA, and I allowed one of them to break apart. Because this is a weak acid, we know a tiny, tiny bit breaks apart, but for the most part, it stays all together. So out of those 12 particles, I just broke up one of them to remind you that a little bit will break apart. So how do I figure out the pH? Well, I haven't added any of the NaOH yet. So really, this is just a weak acid equilibrium problem. So before this beaker, well, you can first of all draw this picture and kind of tell me how much is in there. But before the titration, the pH is going to be determined by the concentration of H plus at equilibrium. So how do I figure that out? Well, those are just my ice tables. So I'm going to do the ice table. I'm going to solve for X. So the Ka of this weak acid must be provided. Solve for X. We know X is the same as the H plus at equilibrium, and to find the pH, we'll take the negative log of the H plus at equilibrium. So this is just your typical Ka weak acid ice problem before the titration has started. So what we're going to do is we're going to you can see this green guy inch, we're going to slowly add OH. Anytime you add a base to an acid, they're going to react, and that's going to produce water and a little of the A minus. And so we can keep going. We react, we use up a little bit of the HA, we produce water and a little more A minus. Same thing, as you can see, my green dot keeps moving. The pH is slowly rising as we add this NaOH because we're using up some of this HA. Anytime you add OH to a acid, you're automatically going to make your water, and in this case, we have that little bit of conjugate base, and it's growing in size and concentration. Keep going. Right, OH using up the HA. Look at, we're having more and more of that A minus, producing still more water as well. Same thing. So we're starting to get closer and closer to the point where maybe we have some conflicting things here. We have a good amount of HA, and we have now a decent amount of that conjugate base A minus. And so now we are at this special point. It's marked with a triangle on your graph, okay? And this is a very special point that we're going to focus on. But as you can see, we've now added OH. There's still some HA, so we're not at the equivalence point yet, because that's when both of these run out. We've added the same amount of OH minus as there was HA in the beaker, but we're at a special point where the HA and the A minus have the same number of moles. So let's talk about what that point is. All right, that point that's marked as a triangle on your graph is called the halfway to the equivalence point. So we're not at the equivalence point, but we are halfway there. And in a weak acid strong base titration, this is a very special point because it means that the amount of weak acid is equal to the amount of conjugate base. So I've literally used up half of my weak acid, and it means I have the same amount of conjugate base produced. So let's think about this. If Ka for that equation is going to be my products, my H plus times my A minus over my HA. So that's how, right, our Ka is always this reaction, my weak acid breaking apart. Right, so Ka is always going to be this equation. Well, what we're saying here is if these two are equal to each other, that part of the equation is essentially equal to 1, right? Let's just say it's 2 molar and 2 molar. Well, 2 divided by 2 gives me that 1. So those are essentially 1, which means I can simplify this equation to what's down below here. If those are 1, well, really it's that what we're saying is that the Ka is equal to H plus. Well, remember pH is equal to the negative log of H plus. And if H plus is the same thing as Ka, right? So if H plus equals Ka, let's just substitute the negative log of Ka. So all I did was substitute. If we know H plus is equal to Ka, I just substituted that into the equation right here. Well, interesting. Anytime we take the negative log of something, hopefully you've seen we've used that letter P, right? The negative log of H is pH. The negative log of OH is POH. Well, the negative log of Ka is called the pKa. So here's the important factor. At the halfway to the equivalence point of a strong base and weak acid titration, the pKa is going to equal the pH. So if I take the negative log of the Ka, that will give me the pH at the halfway to the equivalence point. So for beaker number 2, we are at the halfway to the equivalence point. So in this particular example, remember we started with 12 moles of HA. I've added now 6 moles of the hydroxide. So that means I have 6 moles of HA left. I've also produced 6 moles of A minus, so the fact that these two are equal means we are at the halfway to the equivalence point, okay? Because I've added 6 moles of OH, that means 6 moles have reacted with 6 moles of HA to make 6 waters, and there's no H plus or OH minus excess floating around. So because we are at the halfway to the equivalence point, because HA and A minus are equal, that means the concentration of H plus is equal to the Ka. So to find pH, the pH is equal to the pKa, which, just a reminder, is the negative log of the Ka for that weak acid. So that's how we can find the pH at the halfway to the equivalence point. You'll write down this information, draw this picture, and put these calculations under beaker number 2 on your notes page. All right, so now we're past the halfway to the equivalence point, but we're still not at the equivalence point yet. So I'm still adding hydroxide because my volume keeps increasing that I'm adding, but now I'm using up still the HA, and now I have more A minus, more conjugate base than the weak acid that we started with. All right, so let's look at beaker number 3. And just to be clear, beaker number 3, these calculations here are going to apply for any point, not right at the start, anytime after you've started, anywhere from here to the equivalence point. So we know the halfway to the equivalence point is kind of special, but what we're doing calculation-wise here, we could also do before the halfway to the equivalence point as well. It's the same process. Okay, so anyways, let's say we've added now 8 moles of the hydroxide. So I started with 12 of the HA. I've added 8 of the hydroxide. So that means I've produced 8 water and 8 conjugate base. I only have 4 left over of the HA. I still don't have any excess of this stuff, 0 and 0. So let's talk about how do we solve for the pH at this point in time. Well, we need to do some stoichiometry for this balanced equation right here. and we need to find how many moles of A minus are produced and how many moles of HA are left over. So I'm going to have some excess, and I'm going to have a certain amount produced. I can find the concentration then of A minus that are produced and the concentration of HA in excess using the moles from the BCA table and then dividing those by the total volume. So all I care about now is how much is excess and how much is produced, and we divide those moles in the afterline by the total volume. All right, so then after we have our excess amount, we have a choice. We can either do an ICE table, or we can do something called the Henderson-Hasselbalch equation. So I'm going to show you the ICE table right now because you're familiar with this. And so here's how it would work. We have our weak acid. Oops. No. All right, we have our weak acid breaking apart. And we have a Ka value for that. I can do my ICE table, and now I'm going to find those concentrations. So my concentration of HA initially will go here. My concentration of excess A minus will go here, and we don't have any H plus. So we'll say minus X plus X plus X. So this is going to be some number minus X, X, and some number plus X. And we can plug in, we know the Ka is going to be H plus times A minus over HA. So we can plug all of this in and solve for X. Obviously, the Ka value would be given for this weak acid. So we know then, once we solve for X, that X is the same as H plus at equilibrium, right? That's our value right here. So to find the pH at this point in time, I can take the negative log of H plus at equilibrium. The other option, after we do stoich and find the concentrations of A minus and HA, is we can do something called the Henderson-Hasselbalch equation, which I will show you in a few slides. We're going to keep rolling through the titration, and then I'll talk about your choice to use this Henderson-Hasselbalch equation. All right, same thing here. We keep going. We're adding OH. We are now really diminishing the amount of A minus, diminishing the amount of HA, lots of A minus left over. So we're getting close. You can see the graph is getting steeper. We're getting close to that equivalence point, which is the midpoint of this steep graph. All right, we are now at the equivalence point. So we've added the perfect amount of OH to fully react with the HA. We have a bunch of water that we've produced, and then we also have a lot of this A minus. So let's talk about the equivalence point. Okay, so at the equivalence point, because I've used my HA and my OH minus are fully reactant, there's only water and the conjugate base A minus present. So what happens is we have this secondary reaction of a weak base and water. So this is really my Kb expression, right? Anytime you have a weak base, we put it in water. So that's my Kb expression, where it's my weak base in water makes HA, so the water acts as the acid, donates the HA, and OH minus. So my Kb is going to be HA over OH minus, or HA times, OH minus over A minus. This is a liquid, no liquids in your K expression. So notice the pH here is going to be greater than 7 at the equivalence point because we have a weak base present. So at the equivalence point, it's not only pure water that's present, we also have a weak base present, so we have to do this side reaction, this Kb reaction, to find the pH using the, basically using the weak base concentration. All right, so let's check it out. We've added 12 moles of OH. So I started with 12 HA. I've added 12 OH. They are going to fully react with each other. And so that means we have 12 waters and 12 A minuses, no excess HA, no excess OH, and H plus is not a non-issue in this problem. So we got a bunch of water that we've made, and we have 12 particles of this A minus. So how do I figure out the pH at the equivalence point? Well, we need to do stoich to determine how many moles of A minus were produced and find the concentration of A minus produced using moles from the after line of your BCA table and dividing by the total volume. So essentially we're figuring out how much of this was produced. In this case, I started with 12 and 12, so I must have made 12 moles of this. Divide it by then the total volume, what we started with and what was added. So then, to find the pH, we need to do ice table with a weak base. So whenever you have a weak base, we take that weak base, add it with water, and our equation is always going to be this. And we'll set up our KB expression. Once we have our KB expression and we can plug in our E line of the ice table, we will solve for X, which is the concentration of OH minus at equilibrium, and we can find POH, which is the negative log of OH at equilibrium, and the pH is 14 minus the POH. So this part right here is just my pH square. The only thing is we can't plug in the concentration of A minus directly that we solve from the stoich. We have to do ice because it's a weak base. Remember, if I have a weak acid, its conjugate is going to be, I should say, a decent base. It's not a strong base, but it has basic properties, which is why it's significant enough for us to do this point here. The other thing that you need to know is, how do I get KB? Because most of the time they're just going to give me Ka. So if I know the Ka for the acid, how do I find Kb? Well, Kw, which is 1.0 times 10 to the negative 14th, is equal to Ka times Kb. So I can solve for what the Kb is for the conjugate base by taking the Kw divided by the Ka for the acid. So in order to solve my ice table, I need to know what the Kb is for that conjugate, and all we're going to do is take the Kw divided by the Ka for the acid, and that will give me the Kb to use in my Kb expression when I want to solve for X. All right, so now we are past the equivalence. There's no more HA left. I just keep adding OH minus, and so we have basically a set amount of conjugate, and we just are pretty much washing this or dumping in some extra OH. Still added more, right? No more A minus is added because we're out of this, so really we're just adding a bunch more OH minus. Still going. Even more, you get the idea. All right, somehow I lost my blob of OH. I apologize. There should be a big OH minus circle here because we're in excess, and this green dot is meant to be way up here. So I apologize for that. Okay, we are on beaker number 4, and here's the deal. We have added 16 moles of OH. So we started with 12, we've added 16. So I can only still make 12 and 12 of the water and the A minus because there's no more HA. But that means I'm going to have 4 moles of excess OH minus in here. So how do I figure out the pH when you have this strong base and then this weak base present? Well, we're going to do stoich to find how many moles of OH are excess. In this case, it's 4. We're going to find the concentration of OH using the moles from the stoich that are left over and the total volume. And here's the deal. Yes, there is a strong base and a weak base. So yes, this A minus in theory is impacting the pH. But when you have a mixture of a strong base and a weak base, or let's say you have a mixture of a strong acid and a weak acid, we only care about the strong. This contribution to the pH is so insignificant. As soon as you have excess OH, even if it's just a tiny bit after the equivalence, that is going to determine your pH, not the excess of the weak, or not the produced amount of the weak. So in this case, I just need to find how much is excess. I can then, once I know the excess, it's a strong base, so I can just take the negative log of that concentration of excess. That gives me my POH, and 14 minus the POH gives me the pH. So essentially, after the equivalence point, all I care about is the excess hydroxide. I don't care about the conjugate anymore. All right, so here's a few things. You can see the overall graph here. We have this special point that's basically like for a weak acid, strong base titration. We get kind of this flat level area, then we shoot up, right, and then we level off again. This kind of like middle flattish area, the midpoint of that is the halfway to the equivalence point. Okay, when we shoot up, the midpoint of this line segment is your equivalence point. Notice the equivalence point is greater than 7. There's also a special region when this line is flat here. This is called the buffering region. So I would like for you to label this on your graph as well. So as you can see, the pH here is like a little below 4 and stays a little below 4 for a good amount of time, almost 10 milliliters of the base being added. It stays right below 4 as the pH. A buffer is a solution that resists a change in pH. So even though I'm adding a strong base here, the pH is not changing significantly. So I want you to label that on your graph. We're going to learn a lot more about buffers later this unit, but what you need to know is that the buffering region is when it's flat, the pH is not changing very much. And then I also want you to make a note that the best buffer is at the halfway to equivalence point. And remember, that's when the concentration of your weak acid is equal to the concentration of the conjugate, right there. So yes, this whole region is the buffer region, but the best buffer is at the halfway to the equivalence point. And I promise we'll go more in depth on buffers later this unit. All right, this video was all about a weak acid and a strong base. What if I have a weak base and a strong acid? Well, it's going to be it's just going to be kind of the mirror reflection, right? So we have a starting high, a quick fall, and then we kind of get this flat buffer region. We have our spike, and our equivalence point then is going to be below 7. So when you have a weak acid and a strong base, your equivalence point pH is bigger than 7. When it's a weak base with a strong acid, your equivalence point is a little bit lower than 7. So I basically did a weak acid with a strong base and a strong acid with a strong base. You can see the difference in the graphs. So here's your kind of buffer zone on the weak acid. They have a spike, but the spike is much shorter on the weak acid, and the midpoint, right, our pH on the midpoint of the red graph is going to be around 7. Our midpoint on this graph is higher than 7. And then I also just want you to see the funkiness of the weak base and weak acid. We don't do a ton of that in this class, but you get this kind of hurdle and then a really, really short spike. So not, I don't know, just kind of a funkier shape that we get when you have weak and weak. We focus more on these graphs, but I just want you to see the difference in kind of the shapes. Obviously starting higher, starting lower, but then the size of this pH spike as well that occurs from for those strong versus the shorter size for the weak. All right, so I told you that before we reach the equivalence point, or really I should say after we've started the titration and before we reach the equivalence point, you can do stoichiometry to figure out how much is excess of your HA, how much is produced of your A-. Once you do stoich and have those concentrations, you have two options. You can either do an ice table with starting amounts of both of those items, or you can do an equation called the Henderson-Hasselbalch. Okay, so this is useful for finding the pH of solutions when we know the ratio of HA and A-, which we do in that point of the titration, so after the start and before the equivalence. And so we use it again for weak acid, strong base, or weak base, strong acid titrations after the start and before the equivalence. They can be used in buffer problems and also in indicator problems, which we will see in our next video. So the pH of the solution is going to be equal to the pKa, which remember pKa is the negative log of the Ka for the weak acid, plus the log of the base over the acid. So the conjugate base over the acid, B over A. Okay, so we can use that instead of an ice table if it is easier for you. It's obviously less work than an ice table, but I will say that sometimes kids want one less thing to remember, and we're so used to ice tables that some students prefer the ice table. Some students prefer this just because obviously it's less to plug in to your calculator. All right, so let's talk about beaker like 1, 2, and 3, or really like I would say maybe this is like beaker 1.5 if there was a beaker right after 1 when the reaction starts. So we know beaker 2 is the halfway to the equivalence point. So that's where A- and HA are equal to each other. So that means essentially because these are equal, we're going to take the log of 1, which is the same as 0. So that's why at the halfway to the equivalence point, if this is 0, the pH is equal to the pKa. So the pH is equal to the negative log of Ka at the halfway point. Let's say we're before the halfway point. That means I still have more of my weak acid and less of my conjugate in terms of the ratio. So if I do this fraction, I'm going to have a smaller number over a bigger number. So I'm going to be taking the log of a number that's less than 1. When you take the log of a number that's less than 1, it gives you a negative value. So we're going to be saying that the pH is equal to the pKa plus a negative number. So our pH is going to be slightly lower than the pKa. After the halfway to the equivalence point, I'm going to have more of my conjugate and a smaller number of my weak acid. So big on top, small on bottom. So that means my fraction is going to be a number larger than 1. So when you take the log of a number bigger than 1, you get a positive number. So that means my pH is going to equal my pKa plus a positive number. Okay, so you can see we should have a pH lower than the pKa before the halfway point. I should have a pH bigger than the pKa after the halfway to the equivalence point, and pH equals pKa at the equivalence point. That is a very special point, the halfway, and a lot of questions will be asked about the ratio of weak acid and conjugate if you're before, after, or at the halfway point. So identifying where your halfway to the equivalence point is usually a useful strategy, especially if I'm asking about the ratios, because then you can just identify, am I before or am I after the halfway to the equivalence point. All right, let's work through a practice problem. What is the pH after 13 milliliters of 0.55 molar NaOH have been added to 20 mils of 0.04 molar HC2H3O2, which is acetic acid? So here's the situation. I have NaOH up here, and this is my weak acid. So the strong base, weak acid. And so I have 20 mils down low, and it's 0.4 molar. And up top, I have 0.55 molar, and I've now added, drop-wise, 13 milliliters. So let's solve out this problem. So my first thing is we have to figure out where we are on the graph. So we need to find how many moles of OH have been added and how many moles of the acid are in the flask to start. So I have 0.55 molar of the NaOH, and I added 13 milliliters, so 0.013 liters. I crisscross multiply. That's 0.00715 moles of NaOH, which is the same as the moles of OH because it's 1 to 1. For my acid, I started with 0.4 molar. I have 0.4 molar, and it started with just 20 mils, so 0.02 liters, crisscross, and so I have 0.008 moles of that weak acid. So now we're going to do stoichiometry because this will tell us what we have left over and where we're at in the titration. So here's my balanced equation. My weak acid plus my strong base makes water. And then my conjugate is going to be whatever's left over after we pluck off the H+, so it's the acetate polyatomic. I use my starting moles that we just found. I have none of my products to start, and I don't really care about how much water we're making, so I'm just going to ignore that. So to find X, I'm going to take 0.008 divided by 1, 0.00715 divided by 1. So that's obviously the smaller number, so that means OH limits, so X is going to be that same number, 0.00715. So I plug that in. 0.0080 minus my X gives me how much is excess. 0.00715 minus my X gives me 0. 0 plus that gives me how much is produced. So what I see here is I have excess HA and I've produced some of my A minus, so we're somewhere in this region before the equivalence point. Okay, well, let's look where, who do I have more of? Do I have more of my weak acid or more of my conjugate? I have more of my conjugate. So if I mark my halfway to the equivalence point, we are actually a little bit past, my halfway to the equivalence point. We're actually probably where that blue is because I have more of my A minus than my weak acid. So we've passed the halfway point. If we were at the halfway, these guys would be equal. So now let's find those two concentrations. I'm going to take my moles of excess HA divided by the total volume. So that's my acid. That's how much base we've added. And I take my produced of the A minus divided by the total volume. So here's my concentrations. Oh, look, I already drew that graph. Look, I'm so smart. Okay, so because the molarity of A minus is bigger than H, that means we're past the halfway to the equivalence point, but not at the equivalence point. So now we have an option. We can use those numbers and do ice, or we can do the Henderson-Hasselbalch. So here's my ice table. I take those molarities we just found with my Ka equation, so that's always the weak acid breaking apart. We move towards the zeros, even if there's just one, so minus X plus X plus X. I have my Ka expression. The Ka for acetic acid was provided. I'm going to omit both this plus x and minus x because Ka is small. And then I can solve for x. So I do a little bit of algebra here, crisscross, solve for x, and I get x is equal to 2.14 times 10 to the negative 6, which is the concentration of H plus, and I'll say at equilibrium. So I'm going to take the negative log of H plus at equilibrium, and that gives me a pH of 5.67. Okay, I should also show the 5% rule. Whatever x is divided by this, whatever x is divided by this, make sure it's less than 5%, but this problem's already long, so I'm not going to show that, but you should if this were a problem set or a test. Okay, so that's one choice. The other option is to use the Henderson-Hasselbalch. So you still do your BCA table, you still find the concentration. So you do everything the same really up until this point. And now what we can do is we can do the Henderson-Hasselbalch instead of ice. And so the Henderson-Hasselbalch is that the pH is equal to the pKa plus the log of the base over the acid. So I can take the negative log of the Ka, which is pKa, plus I found these concentrations. Here's my base, here's my acid. So I'm just going to plug in Ka, plug in those molarities I found above, and I get a pH of 5.67, same answer. So it is your choice if you like to do the ice table or the Henderson-Hasselbalch when you are somewhere before the equivalence point. All right, here's a fun problem. Pause the video and read it for me. Okay, so the first question says, find the Ka value for this acid. Well, here's what we know. We know that the equivalence point was at 20 milliliters. So here was my equivalence point. So if 20 mils got me to the equivalence, then 10 mils must get me to the halfway to the equivalence. Right? 20 is the full equivalence, half of that would be 10. And at the halfway to the equivalence point, we know that the pH is equal to the pKa, and I have the pH. So the equivalence point is useful, or the halfway to the equivalence point can be really useful. It can actually help you find the Ka of an acid if you know the pH value at the halfway to the equivalence point. So at the halfway to the equivalence point, the pH was 3.44, so that means 3.44 equals pKa. Well, to find Ka, then we got to get rid of that P, so we'll take 10 to the negative pKa, just like we take 10 to the negative pH to get H. So 10 to the negative 3.44 gives me my Ka, so my Ka value for this weak acid is 3.6 times 10 to the negative fourth. And I was able to use the halfway equivalence point to figure that out. Letter B says the pH of the solution after the total volume of 25 milliliters has been added. So that's what we're trying to find. So after the equivalence point, because 25 mils is going to be past the 20 mil equivalence point, we know that the pH is determined by the excess OH. So let's do some stoich. We know the moles of acid because they told me it was 2.00 times 10 to the negative third moles in the problem. And we can then say, well, if I have 0.1 molar NaOH and I added 25 mils, I can find moles of NaOH, which is the same as moles of OH. So I have those starting amounts, don't really care about water. And then we have O minus. Okay, so we can solve for x. This guy divided by 1, this guy divided by 1. We can see the HA limits, so there's none left over. 0.0025 minus 2.0 times 10 to the negative third, which is my x, gives me the remaining, and it gives me how much is produced. So I have two bases present, the OH and the excess OH and the produced A minus. But because OH is strong and A minus is weak, the pH is only going to be determined by the excess OH minus after the equivalence point. So I can take my moles excess divided by the total volume, so that's the acid volume and how much base was added. So I have my molarity. So then the POH, negative log of OH, I can take that POH and subtract it from 14 to get my pH at the point after the equivalence. All right, pause the video for me. I want you to try this practice number 3 on your own. I'll put the answer up in 3, 2, 1. All right, so first thing is to write the equation of the weak base with the strong acid. And so all I'm doing is giving that H plus over, or you could add it with H3O plus if that makes you feel better. Give away the H, so that would give me the NH4 plus and H2O. Either one is acceptable for your weak base strong acid titration. So here's what I'm looking for your graph. It should obviously start high and end low. The initial pH, again, should be bigger than 7 because it's a base. The equivalence point should be 15 milliliters of HCl. The pH at the equivalence point should be less than 7. And then halfway to the equivalence point would be when we have 7.5 milliliters, right? Because if 15 is the equivalence, 7.5 is halfway. And I can actually put roughly where the pH is at that point, so where this halfway to the equivalence point is, because I know that Ka is Kw divided by Kb. So I can solve for the Ka, and the pH at the halfway equivalence is the pKa. So if I take the negative log of Ka, that will give me the pH at this halfway to the equivalence point. All right, last one is a multiple choice I want you to try. So we have a monoprotic acid, meaning it's HA, right? Mono, meaning it's just bonded to one thing with a strong base. And we have the graph, but I want you to tell me the pKa and the concentration of NaOH that was added. So try to figure this one out. I'll put the answer up in 3, 2, 1. All right, so first of all, at the equivalence point, we know that 20 mils were added. And so if I have 0.1 molar acid and 20 mils, I can figure out how many moles of acid. And at the equivalence, moles of acid equals moles of base. So I know that if I had 0.002 moles of acid, that means at the equivalence there was 0.002 moles of base and 20 mils were added. So I can figure out the concentration of OH minus. And then at the halfway to the equivalence point, the pH equals the pKa. So if I find that the pH was, I don't know, 4 point something, almost 4.5, 4.7 maybe, that means the pKa equals the pH at the halfway. So letter B is your best choice because the pKa is 4.7, that's the pH at the halfway, and then 0.1 molar is what we get at the equivalence point. So kind of two things to look at, the equivalence and the halfway to the equivalence on this multiple choice question. At this point, you've seen some practice. You should be able to do the weak acid strong base titration problem on objective number 3. It is worth 6 points, I believe, 1 point per section because you're calculating the pH at different points along the curve. That takes a lot of time. So I'll give you 6 points for doing that entire problem.